Hey, welcome back. We are now going to do the review for differential equations for the final exam. Okay, so final exam review. So I'll be taking, I'll be giving you sort of sets of questions from WebAssign that you should go and take a look at. So 1.1, I'm not going to include everything on the test. So just mostly stuff that we've already seen on tests 1, 2, 3, maybe one extra thing that we have to take care of. But anyways, sort of give you a reminder of what we've been doing, and then give you these question pools and maybe do one or two questions from every section. Okay. Okay, so 1.1, we introduced this idea of a differential equation. Before we gave you the tools for solving differential equations, we just wanted to verify whether or not they were actually solutions. So here we have a differential equation and a potential solution. This is back before we knew how to find something like this. What I want to do is basically show that this satisfies, the solution satisfies this differential equation on some interval. And if you remember, there was this whole thing on intervals of definition. There's the domain of the actual function, and then there's the interval of uniqueness and existence and uniqueness. Okay, so all of those three intervals are kind of on the table. I probably won't worry about the interval of uniqueness and existence. That was where you had to take partial derivatives of the you had to look at f of x, y, if it was set up in the form dy with respect to t equaling some function. I guess here's f of t y. Oh my god. Sorry. Where was I? Just sort of had to. Some guy with a chainsaw out my. And I lost my pen. Okay. Okay, so anyways, here we are, 1.1, differential equation, potential solution. I got to find the interval on which this thing will work. And so the way I want you to do it is left-hand side, right-hand side. Okay. So you need you're going to need the derivative to get this to work, so you might as well get the derivative as well. Derivative of 8/5 is 0. The derivative of negative 8/5 e to the negative 30t. That's going to give you negative 8/5 e to the negative 30t, and then the chain rule, negative 30 tacked on there. You simplify that, so y prime will be 5 goes in the 30 6 times. 6 times 8 is 48 e to the negative 30t. And then you're going left-hand side, right-hand side. Okay. Right, so the left-hand side, I should have gave myself more room, but it would be dy over dt plus 30y. So you're just working with this side and rewrite it using the given information, which is basically all of this stuff that you got from the book and from calculus. So I have 48 e to the negative 30t plus 30 times y, which is 8/5 minus 8/5 e to the negative 30t. And then that will equal 48 e to the negative 30t plus 5 goes in the 30. 6 times 8 is 48 minus 48 e to the negative 30t. These cancel, so that left-hand side is just 48. The right-hand side then, is 48. So it looks like these are both equal. There were no restrictions on this process, so you could say the interval on which this will work will be from negative infinity to infinity. And so it is a solution. Okay. Let's look at another one. So this one a little harder. Number 9, we have y minus x times y prime equals y minus x plus 2. And then I have y equals x plus 2 times the square root of x plus 5 as our potential solution. Let's rewrite it so I can work with it. So I have x plus 2 times x plus 5 to the 1/2. And then I'm going to need the derivative. So y prime will be 1 plus 2 times, so first power rule, bring down the 1/2, and then I have x plus 5 to the 1/2 minus 1. 1/2 minus 2/2 is minus 1/2, and then chain rule just times 1. Clean it up a bit. So I'll have 1 plus basically just a square root of x plus 5. Whoops, but it's to the negative 1/2, so it's 1 all over that. Okay. All right. As far as the interval of definition for this, that's kind of the funny part. Originally, the function has a domain that you kind of want to look at. The domain, we just need x plus 5, the stuff inside the square root, to be greater than or equal to 0. Right? In other words, we need x to be greater than or equal to negative 5. But the interval of definition, we need to make sure that both y and y prime will work. Right? So here I also then need to consider this domain and consider kind of the overlap with the domain of the original function, right? So this domain has issues not just when you put a negative in the radical, but you also can't put a 0 like in the denominator. So we need to make sure here that x plus 5 is strictly greater than 0. In other words, we want x greater than negative 5, and that'll become your interval of definition. Right, so your big I is going to be from negative 5 to infinity. Okay, so for the interval definition, in case you've forgotten, it's going to be, and let's get the official documentation from the book. The function, the original function, has to be defined, and all of its derivatives up to the order of the differential equation need to be continuous. Okay, so that's our interval of definition. Let's find it in the book just to make sure I'm not misleading you. The solution. Yeah, so any function phi defined on an interval I and possessing at least, so it has to be defined on this interval, and it has to have the same up to the order. So in our example, the order of that differential equation is 1. So I need to make sure that first derivative is also continuous on this I, and that it works when you substitute it into the original differential equation. Okay. So the big issue with this problem is that right there, this interval of definition is not exactly the same as the domain of the original function. Okay. From there, we can go to the left-hand side, right-hand side stuff, and get that out of the way. So on the left-hand side then of your differential equation, remember that's the left-hand side, and so I have y minus x times y prime, substituting in then the given information, which is kind of this stuff right here. I have y, which is x plus 2 times the square root of x plus y, minus x times y prime, which is going to be 1 plus 1 all over the square root of x plus 5. I'm going to simplify that. It's not a bad idea to get the right-hand side and kind of just look under the hood and see what it is, so you can get them to kind of match up. Y minus x plus 2 sitting right there. So I have y as x plus 2 square root of x plus 5 minus x plus 2. And then simplifying that, that'll be 2 square root of x plus 5 plus 2. All right, so let's see what we have on the left-hand side, right? So first I can simplify that term. X minus x is 0, so I just have 2 square root x plus 5 times 1 plus 1 all over the square root of x plus 5. Okay, I'm going to distribute this, and I'll have 2 square root of x plus 5. In the second distribution, the square root of x plus 5s will cancel, and you'll just have 2. So here, both of them will be good on both sides. We already kind of worried about the interval of definition above. So ultimately then you could say this thing is a solution on that particular interval. Okay, so hence y given, the solution given, and I have to sneeze. Okay, false alarm. Hence y given is a solution on the interval that I mentioned above. Okay. So you have to do the left-hand, right-hand side thing, and you have to note the domain of definition. Okay. All right, let's move into 1.2 then. 1.2, we were finding particular solutions to differential equations. We're looking at problems like 1 to 7 from WebAssign. Okay, so at first we have problem 2. They give you the differential equation y prime, which you don't even really need, but they give it to you anyways. We have y equals 1 all over x squared plus c, and then the initial condition y of 3 is 1/5. Okay, so we want the particular solution. In other words, we're basically just going to take that initial condition and plop it into this guy right here. Okay, so we'll get 1/5 equals 1 all over 9 plus c. Cross multiply, you get 9 plus c is 5. And then finally c is -4. So our particular solution is going to be y equals 1 all over x squared minus 4. Again, we need to make sure that the thing is defined and that the derivatives are continuous up to the order of the differential equation. So the order of the differential equation, of course, is 1. So I need the first derivative. So y prime would be negative x squared minus 4 to the -2 times 2x, which of course is -2x all over x squared minus 4 squared. Okay. All right. So both of the functions, the derivative and its original function, had the same issue at whenever x squared minus 4 is 0. That's the troublemaker. So we just need to make sure that that's not the case in our interval of definition, and we need the interval that contains the x coordinate 3 above, okay, from the initial condition. Okay, so anyways, where's this thing going to equal 0? Well, you could do the square root property, set it equal to 4, and then x will be plus or minus 2. So the domain of the solution is going to be -∞ to -2 union with -2 to 2 union with 2 to infinity. But the interval of definition, which is what I need for the last part for full credit, I need the interval that contains the initial condition. So I need the interval that has 3 in it. So x equals 3 is in the rightmost interval. That will be my interval of definition. Okay. Okay. Let's look at another one, number 5. So I have y double prime minus y equals 0. The solution, the general solution, c1 e to the x plus c2 e to the -x. Y of 0 is 1, and then y prime of 0 is 8. The order is 2, so I need to make sure that my derivatives up to the second derivative are nicely behaved with regards to continuity. So I'm just getting the derivatives here. And of course they're exponential functions. They are continuous everywhere. There's not going to be any issues here. The interval of definition will just be everything, all real numbers from -∞ to infinity. Okay, now I need my particular solution, so I'm going to plug these guys into this formula and then into this formula here. So firstly, y of 0 is 1, so I'll put 1 in for y. Then equals c1 e to the 0 is just 1, so c1 times 1 is c1, plus c2 times e to the 0 again is just 1, so it's c1 plus c2. Okay. Then use the other initial condition in the derivative equation, so I'll have 8 for y prime equals c1, and again it's e to the 0, right? E to the 0 is 1, so c1 times 1 is just c1, and then minus c2 times e to the 0, and again e to the 0 is just 1, so c2. Okay, great. Here you have a system of equations you need to solve for c1 and c2. And you could use the addition method, use the substitution method. I'm going to do the addition method just because I can see the C2s are going to cancel. So I get 9 equals 2C1. In other words, C1 equals 9 halves. Then I could use this first equation and rewrite it as C2 equals 1 minus C1, and then substitute in 9 halves. So C2 will be 1 minus 9 halves, which will be 2 halves minus 9 halves, which will be negative 7 halves. So my particular solution is going to be y equals 9 halves e to the x minus 7 halves e to the negative x. Okay. So enough of that. Finally, in 2.2, we have our first method for solving differential equations, which was separation of variables. Okay, so I'll be thinking of questions like 1 to 14. Let's look at a trig version that's kind of written in the differential form. Cosecant y dx plus secant squared x dy equals 0. Okay, so I'm going to divide everything by dx. I get cosecant y plus secant squared x dy over dx. I want to isolate all the y stuff on one side, all the x stuff on the other, right? Well, I guess I shouldn't have divided by dx just yet. Well, okay, whatever. All right, secant squared x dy over dx then equals negative cosecant y. Okay. Secant is the same as 1 over cosine. So I have 1 over cosine squared x times dy over dx equals negative 1 all over sine of y. This cosecant's 1 over sine. Then I'm going to separate, right? I need to get the y stuff on one side, so I'm going to multiply both sides by sine y. I'll leave all the constants on the right. I'm going to multiply both sides by cosine squared, multiply both sides by dx, and you get sine y dy equals negative cosine squared x dx. Okay, I'm going to integrate both sides. So over on the left, I get negative cosine y. Over on the right, I'll have negative, and I'm going to have to do 1 plus cosine 2x over 2, a power reduction formula. Okay, so I got negative cosine of y equals, splitting this up into two integrals. We'll have negative cosine y equals negative 1/2 x minus, this will be sine of 2x, and if you have a u sub, it would be a factor of 1/2, so it would be sine 2x over 4, and then plus your integration constant. There's no real nice way to isolate y. I guess you could do like multiply both sides by a negative and cosine inverse on both sides, but this is a fine answer. This works for me. Okay, so you can leave your answer there. Okay, on the other hand, if you have like absolute values in your answer, you need to get rid of those. So for number 13, that's kind of an example of that root. I have x squared times dy over dx equals y minus xy, and my initial condition y of negative 1 equals negative 4. Okay, so I need to separate. So on the right hand side, I'm going to factor out a y, and then I'm going to divide both sides by y, divide both sides by x, multiply by dx. You get dy all over y equals 1 minus x all over x dx. Okay. Then I need to integrate, and you see I get ln absolute value of y on the left, and on the right, you're going to want to sort of rewrite it. And then you'll have ln absolute value of y equals ln absolute value of x minus x plus c. Whoops, and I copied the problem wrong. It should be x squared. So I screwed that up. Sorry about that. I didn't copy it wrong. I just lost the square. So I have x to the negative 2 minus x over x squared will be 1 over x. Okay, so I'll end up with x to the negative 2 plus 1 will be x to the negative 1 divided by negative 1 is negative 1 over x at the end of the day. And then the next guy is a natural log. Okay, this time you do not want to leave your answer this way. You want to exponentiate to get rid of the natural logs and eventually get rid of the absolute values as well. Okay, so I'm going to exponentiate. On the left, I'll have the absolute value of y. On the right, I'm going to break it up a little. I'll have e to the negative 1 over x times e to the negative ln of the absolute value of x times e to the c. Okay. All right. The second term you're going to do a power rule on. So you're going to take this negative and plop it inside the natural log. And you get the absolute value of y equals e to the negative 1 over x, and then e to the ln of the absolute value of 1 over x, and then e to the c. Okay, the exponential and the logs here will cancel, and so you'll be left with right now, as of now, e to the c times e to the negative 1 over x times the absolute value of 1 over x. Now you want to drop the absolute values, replace with a plus or minus on the right side, so you get plus or minus e to the c, e to the negative 1 over x times 1 over x. And this part just becomes a big old constant, right? So I'll have y equals c, e to the negative 1 over x times 1 over x, or you just put the whole thing over x. We're not done. We have an initial condition up at the top. So I need to substitute that in. For y is negative 4, and then x is negative 1. So c, e to the negative 1 over negative 1 is just 1, and then that's all over negative 1. Multiply both sides by negative 1, you get 4 equals ce. So c will equal 4e to the negative 1. So my final answer, y equals 4e to the negative 1 times e to the negative 1 over x all over x. Or if you would rather, y equals 4e to the negative 1 minus 1 over x all over x. Okay. Okay. The next part then in 2.3, we start worrying about integrating factors, the mu constant that we multiplied by. I'm looking at questions like 1 to 20. So in particular, let's look at 17. X times dy over dx plus y equals 2x plus 1. The initial condition, y of 1 equals 9. Okay, so the first thing you need to do is get it into the appropriate form. So the appropriate form, if you remember, is dy over dx plus p of x times y equals some f of x, right? All right, so I need to divide everything by x. So I get dy over dx plus y over x equals 2 plus 1 over x. The integrating factor is from px. We need px and f of x in order to figure out our interval definition. P of x is 1 over x. F of x is 2 plus 1 over x. So our interval of definition is going to be the intersection of the domains of those two functions. In particular, it's from negative infinity to 0, union with 0 to infinity, but we want the initial condition, the x value, we need it to be, so if the domain is from negative infinity to 0, union with 0 to infinity, I need to pick the interval that has 1 in it. Okay, I need to pick, in this case, the right interval. Okay, so our interval of definition, you could state it right here, is going to go from 0 to infinity. Okay, because both domains have that issue of division by 0. Right, now we're going to go ahead and get our mu. So mu is e to the integral of 1 over x dx, e to the integral of px. That then will be e to the ln of absolute value of x, but because we're in the positive interval, we could just write x. The e and the ln will cancel, and you just get an integrating factor of x, which kind of gets us right back to where we started. As multiplying through, you get x dy over dx plus xy equals, whoops, I'm multiplying on the wrong equation. I want to multiply this second equation by x. And that's why I say you get back to where you started. X dy over dx plus y equals 2x plus 1. Yeah. Then you could collapse the left-hand side into the derivative with respect to x of mu, which was x times y. On the right-hand side, you just have the 2x plus 1. Then you integrate both sides with respect to x, and you're going to get xy equals 2x squared over 2 is x squared plus x, and then plus your integration constant. You could divide by x. Finally sneezed. So you're going to get y equals x plus 1 plus c over x. Then you use your initial constant to find c. So y of 1 is 9. So 9 equals 1 plus c over 1, which is c. So c is going to equal 7. And then you could build your solution. Y equals x plus 1 plus 7 over x on the interval from 0 to infinity. Okay, let's try one more, but the piecewise type. So I'll definitely put a piecewise one on the final. We have dy over dx plus y equals f of x. Initial condition, y of 0 is 1. And then f of x is a piecewise function, 1 when x is in between 0 and 1. And then negative 1 when x is in between 1 and infinity. So whenever x is greater than 1. Okay, so what happens in these problems? You have basically two differential equations to solve, and then you have to make sure that they are continuous, right? You want to make sure that they hook up at this position, not at y of 0 equals 1, but rather when x is 1, they both are equal to the same thing. Okay, so when x is 1, you want both of them to be equal to 1. Okay, so the first differential equation, you use the first piece of the function, so you set it equal to 1. So dy over dx plus y equals 1. And here the integrating factor mu is e to the integral of 1 dx. So you just get e to the x, multiply through, collapse, you get the derivative with respect to x of mu, e to the x times y. On the right hand side you have e to the x. Integrate both sides with respect to x. You get e to the x y equals e to the x plus c. Divide everything by e to the x, you get y equals 1 plus c e to the negative x. Use the initial condition to complete the picture. So using y of 0 equals 1, I have 1 equals 1 plus c e to the 0. In other words, 1 equals 1 plus c. In other words, c just equals 0. Plugging 0 back into the general solution there, you get 1 plus 0. So y is just 1, right? Because if you plug 0 in to here, you just end up with 1 plus 0, so y is equal to 1. That becomes kind of the initial condition for then the other differential equation, right? So y of 1 we want equal to 1. Okay, you kind of carry that condition on. That'll ensure that the two equations, the two functions connect at that point, because we want continuity. Okay, all right, so this differential equation then is dy over dx plus y equals this other piece, negative 1, from the piecewise definition. And so our integrating factor this time, again, is the same thing, e to the integral of 1 dx, which is e to the x. Multiply through, collapse, you get the derivative with respect to x of y times e to the x equals negative e to the x. Integrate both sides, and you get y e to the x equals negative e to the x plus c. Divide by e to the x, you get y equals negative 1 plus c e to the negative x. Okay, now use the second initial condition that we formed to ensure continuity. That's right here. Okay. So y is 1, and then x is 1 as well. So CE to the negative 1. Subtract 1 over, you get negative 2, and then CE to the negative 1. Multiply both sides by e to the positive 1, and you get C is negative 2e. And then plop that in to complete your second part. Y is negative 1 minus 2e times e to the negative x. Okay, or if you would rather, and it seems like I made a mistake, it should be plus 2 up here. So this is plus 2. So at the end of the day, let's rewrite this because it looks a little weird with the e times e to the negative x. It's really e to the 1 times e to the negative x. So that'll be negative 1 plus 2 e to the 1 minus x. And so finally, our solution in its two pieces is 1 when x is in between 0 and 1. And then it's negative 1 plus 2e to the 1 minus x when x is greater than or equal to 1. Okay, and that would be your final answer there. Okay, so expect one of those. Set 2.4 then is getting into exact equations. Okay. Was this guy back here an exact equation? Was that kind of the punchline because we had to go back and forth? Well, I guess we wouldn't be able, it's not, is it? Because you would have to set it somehow equal to 0, but you multiply everything by dx, and you would have x dy plus y dx equals 2x dx plus 1 dx. Move all the dx to the other side, so get x dy plus y minus 2x minus 1 dx equals 0. To see if it's exact, you do the partial derivatives, right? So the partial of m with respect to y is going to be 1, and then the partial of this thing with respect to x. So that one isn't exact, is not, but they're in a wrong order, right? So it should be dx first. So this one with respect to y is 1, and then the other guy with respect to x, yes. So that was exact. That's probably what happens when you have something that that's exact already. You technically don't even have to bother with the integrating factor, right? We could have just started right here and then skipped to right here. But that only works if it's exact, right? So speaking and then, so I believe that was exact, right? So let me take this again and kind of take it over here and rewrite it. Y minus 2x minus 1 dx plus x dy equals 0. So the partial of this thing with respect to y is going to be 1, and then the partial of this thing with respect to x is going to be, so I speculate that that's what happened there. Because it was exact, you would have your integrating factor doesn't really make a difference in the big picture. Doing all this work is for nothing, right? But anyways, let's go into the section on exact equations and kind of get a refresher course on that. So problems like 1 to 10 and WebAssign, they're always set up in this differential form. So you have 4t cubed y minus 21t squared minus y dt, and then plus t to the 4th plus 3y squared minus t dy equals 0. Okay, so the spiel was we predict that these things are the results of taking partial derivatives of some ultimate potential function on the top of the pyramid, this f of xy. So if you took the derivative of this with respect to x, you would get the left part, or in this case with respect to t. If you take the derivative of this with respect to y, you get the right part. Okay, and so we have this kind of process for figuring out what is f of x, y, and that's what we're after. In this case, it's f of ty, though. Right. Okay, so let's make sure it's exact. So I have to take the derivative of this first guy with respect to y. Okay, so it's going to be 4t cubed minus 1. And then take the derivative of this guy with respect to x, or in this case t. Okay. And in this case, it's 4t cubed minus 1. So these are the same, so it's exact. Okay. Okay, so if that works, then in order to retrieve this thing they call a potential function, what you need to do is integrate with respect to t. So I'll integrate m with respect to t, and then you're going to take the partial derivative of that with respect to y and set it equal to n. Okay, so I do the partial derivative of this thing with respect to y and set it equal to n, right? Okay, so let's do that. So I set up my partial derivative with respect to y of the integral of m, which is 4t cubed y minus 21t squared minus y dt. And on the right-hand side, you just put n. So I put t to the fourth plus 3y squared minus t. All right, so if you integrate this, you get basically your solution. It's just it's not all there. So if I integrate that with respect to t, I'm going to get 4t to the fourth over 4, which is t to the fourth, and then times y, minus 21t cubed over 3, so 7t cubed, and then minus yt. And then don't forget, you have to add in this stuff that may have been annihilated by taking the derivative with respect to t. All right? Okay, on the right-hand side, you have t to the fourth plus 3y squared minus t. So this chunk right here is the solution. The only problem is I don't know what g of y is, so I have to figure that out using this equation. So take the derivative with respect to y, you get t to the fourth minus 0 minus t plus g prime of y. Okay. Okay, so the t to the fourth will cancel, the t's will cancel, and you just get g prime of y, a differential equation, right? G prime of y equals 3y squared. Integrate both sides with respect to y, and you get g of y equals 3y cubed over 3, which is y cubed, and then plus some constant. All right. So plugging that back into our formula here for what we think f of ty is, we get f of ty equals t to the fourth y minus 7t cubed minus y times t plus y cubed, and usually we could put the constant on the other side, so I put a k over here. Set the thing equal to k. All right. So that's exact equations. Let's look at 4.1 now. And now we're dealing with higher order differential equations. You know, mixed in between, we had a lot of applications, and I don't mean to not emphasize how important those applications were, but I'm not going to put those sections on the final exam. So if I'm not including it in my review, I'm not including it on the final exam. Okay, so anyways, 4.1 begins with us trying to determine the solution set for differential equations. And our workhorse was the Wronskian, right? So number 13, they give you a set of equations, and then a differential equation, which really isn't important, and then an interval. I mean, the differential equation can be important because if it was order 2, it clearly would not be independent because you have too many functions. You only need 2 functions for a differential equation order 2. Right. But anyways, let's get this one. This one is kind of nasty, as I recall. So let's look at it. We need to make sure the Wronskian is not equal to 0. That's kind of like making sure that you don't have division by 0 in the world of linear algebra. Okay, making sure your determinant is not equal to 0. It just allows you to solve a system of equations. Okay, I never teach that class. I would like to one day, but maybe when I'm older. I'm pretty old now, but when I'm way older. Okay. So here we are. We set the functions across the first row and then take the derivatives, right? So this would be 1 and then 0. This would be negative 6x to the negative 7 and then 42x to the negative 8. Need a product rule for this guy, so it's going to be x to the negative 7. The derivative ln x is 1 over x. X to the negative 6 times x to the negative 1 is x to the negative 7. and then plus negative 6x to the negative 7 times ln of x. And then take the derivative of that. We get negative 7x to the negative 8 plus 42x to the negative 8 ln x, and then minus 6x to the negative 8, and then combine like terms on that guy. And looks like we're getting 42x to the negative 8 ln x minus 13x to the negative 8. Okay, just so I don't make any mistakes, I'm going to kind of scribble this part out so I don't accidentally look at that. Okay, so now I need to take the determinant of this, and the way it works with 3 by 3s is first you write down that guy there. Okay, so I'm going to write down x times the determinant of sort of this box. Okay, so you're multiplying on the columns and subtracting. So I have negative 6x to the negative 7 times that 42x to the negative 8 ln x minus 13x to the negative 8. Okay, so what is that going to be? It's going to be negative 6 times 42 is negative 252. X to the negative 7 times x to the negative 8, you add the exponents. So that'll be x to the negative 15. Then you get ln x. And then minus, but there'll be a negative in there. Where the heck am I? I'm still on the first multiplication. So it'd be plus negative 6 times negative 13 is plus 78 x to the negative 15 again. And then minus the diagonals, the other diagonal multiplied out. So you'd have 42x to the negative 15. And then minus 42 times 6, right, is another 252. But yeah, so minus 252 x to the negative 15 ln x. Whew. Okay, that's the first term. Then you go to the second column, and you use this guy and the determinant from this portion in blue, the diagonal on those. So that times that, minus that times that. Okay, but on the second term, you're always putting a minus in front of everything. So second term will be minus x to the negative 6 times 1 times 42x to the negative 8 ln x minus 13x to the negative 8, and then minus 0. Okay, so at least that works out kind of nice, if nothing else does. Then I go to my third column, and I write down the x to the negative 6 ln x, and I'm finding the determinant of this portion. Okay, so that would be plus x to the negative 6 ln x times just 42x to the negative 8. That's it, minus 0. Okay, so now I just clean all that junk up. See if there's any cancellation. So clearly this thing and this thing will cancel out. And I'll just have 78 minus 42 times x. 78 minus 42 is 36. I'll have 36x to the negative 15 times x. That will be 36x to the negative 14. And then the next one I'll have minus 42x to the negative 14 ln x, then plus 13x to the negative 14, and then plus 42x to the negative 14 ln x. And then these guys will cancel, and you're just left with 49x to the negative 14. And now the interval they give you becomes important. I only consider that interval. So on that interval, that will never equal 0, right? Because there's no way to make that, you can't put 0 in there. And if you could put a 0 in there, it wouldn't work. It'd just be undefined. But anyways, on that interval, on the interval from 0 to infinity, it's never equal to 0. And that tells us it's independent. It's ready to leave its parents and live on its own. Okay, so the set of functions is linearly independent. And so if we have a third order differential equation, we can say its general solution, and sometimes I'll ask for the general solution then if it is independent. Y will equal C1 x plus C2 x to the negative 6 plus C3 x to the negative 6 ln x. Okay, so that would be that. Let's move on to 4.3, and now we're dealing with higher order differential equations, linear differential equations with constant coefficients. And this is where I'm going to expand on what we did on the test. I'm going to include higher order, so make sure you can do synthetic division if you need to. Okay. So for example, number 13, I have 16 fourth derivative with respect to x plus 48 times the second derivative with respect to x plus 36y. So first you get the auxiliary equation, so 16m to the fourth plus 48m squared plus 36. And then you want to solve this equation. I can divide everything by 4. So get 4m to the fourth plus 12m squared plus 9 is 0. I don't even need the synthetic division here. So 2m plus 3, 2m squared plus 3, and then 2m squared plus 3. So you have some repeated roots. The original root then, 2m squared plus 3 is 0. So 2m squared is negative 3. So m squared is negative 3 halves. So m is plus or minus square root of 3 halves I. Okay, and then it's repeated, right? So you also have plus or minus square root 3 halves I. So you have to remember all your forms. If you have imaginary solutions, you're dealing with the kind of the Euler formula, e to the I theta times C1 cosine. They call it beta t plus C2 sine beta t. And then if it's repeated, you have to tack in an extra x or an extra t, depending on what you're dealing with. So in this case anyways, we have then y equals e to the 0 is just 1, then times C1 cosine of root 3 over 2t plus C2 sine of root 3 all over 2t. Or is it x? It's x in this. It doesn't really matter, but I wouldn't take off points for that. Something silly, but x and then plus c2 sine of 3, the square root of 3 all over 2x, and then some repeated parts. So c3, and you have to tack in an x, right? X cosine square root of 3 all over 2x plus c4 x sine of square root 3 all over 2x. Okay, let's look at one more of those. Hopefully you have to do synthetic division on this one. It's number 10. The third derivative of u with respect to t plus the second derivative of u with respect to t minus 2u equals 0. Get your auxiliary. So this will be m cubed plus m squared minus 2 is 0. Then probably synthetic division, right? You could guess at the root. So it's usually 1, negative 1, 2, negative 2, something simple like that. And if you remember your pre-calc, it's all dependent on this number and the leading term, and it will be some factor of those. So it's either 1 or 2, or negative 1 or negative 2. So you try 1. It looks like 1's going to work, right? You could do synthetic division on it. So you have 1m cubed, 1m squared, 0 m's, and then negative 2 is your constant. And you bring down the 1, and then you multiply 1 times 1 goes here. And then you add, so this will be 2. And then 1 times 2 goes here. 0 plus 2 is 2. 1 times 2 is 2, goes here. Negative, yeah, that works. If you get 0 right there, it works. Okay. So our factorization will be m minus 1 times, and then from this information, 1m squared plus 2m plus 2 equals 0. Okay, then this guy, I don't think I can factor it, so I have to go to quadratic. So I get m equals negative b, negative 2, plus or minus the square root of b squared, 4 minus 4 times a times c. Don't be the person who forgets the quadratic formula. Don't be that guy. All over 2 times a. It's just 2. So this will be negative 2 plus or minus the square root of 4 minus 8 is negative 4 all over 2. There's an imaginary part then. Negative 2 plus or minus 2i all over 2 equals negative 1 plus or minus I. Okay, so our roots from the auxiliary equations here, in this case, m equals 1 and negative 1 plus or minus I. Okay, so we're going to get y equals c1 e to the 1t, e to the t, plus e to the negative t times c2 cosine of t, 1t, and then plus c3 sine of t. And that would be your answer. Okay, moving on. The next part, of course, is our favorite part, the undetermined coefficients type problems. So these are linear, non-homogeneous differential equations with constant coefficients. Right? Looking at problems like 12 to 21, let's look at number 20. That looks fairly annoying enough. I have y double prime plus 25y equals 10 sine of 5t. Okay, so you got two differential equations, kind of. The first one, you get the solution to the associated homogeneous differential equations. Set it equal to 0. Get the auxiliary, solve. Okay, then we have our complementary solution. So this will be c1 cosine 5t plus c2 sine of 5t. Okay. Then we consider the annihilator for this portion and form a new differential equation. Right. So the annihilator for this is exactly the same as the other annihilator. The roots that would have created this 10 sine 5t would be m equal plus or minus 5i. Right, so our annihilator for that portion would be d squared plus 25. So originally it's d squared plus 25 equals 10 sine 5t, but then when you add on or tack on, or however you want to think of it, multiply in another differential operator, d squared plus 25, that will effectively make the right-hand side 0. Which is what you want, because we know how to deal with these homogeneous differential equations. So in this case, the roots, of course, will be plus or minus 5i, and then repeat it, plus or minus 5i. So our solution to this part of the problem, y equals, what do we have? So c1 cosine 5t plus c2 sine 5t, that's the complementary part, and then the rest should be the particular. So plus c3, and we need to tack in a t because of the repeated root. c3t cosine 5t plus c4t sine 5t. Okay. Then I'm going to replace the c3, c4 with a and b and form my potential particular solution. So this will be at cosine 5t plus bt sine 5t. And then I could cruise through and get my information, right? Okay, so yp prime is going to be, first I'll take the derivative of the t portion. So I get a cosine 5t plus b sine 5t, and then I'll take the derivative of the trig parts. So I'll get minus 5at sine 5t plus 5bt cosine 5t. Okay, then I need the second derivative. So taking the derivative of the first portion, I get negative 5a sine 5t plus 5b cosine 5t. And then taking the derivative of this part, I'm going to have to do product rules, so I'm going to get 4 more terms, right? So I'm going to get first taking the derivative of the t portion, negative 5a sine 5t plus 5b cosine 5t. And now taking the derivative of the trig portion, I get negative 25at sine 5t. Whoops, that should be a cosine 5t. Cosine 5t minus 25 bt sine of 5t. Okay. Then I need to plop that information back into the original differential equation and solve for a and b. So the original differential equation was y double prime plus 25y equals 10 sine 5t. Okay, so looking at y double prime, and then y, so 25 times yp, if we want to play this game where I kind of just cheat a little bit, I would get 25at cosine 5t plus 25bt sine 5t. And then if you add that to y double prime, look what's happening. It's going to cancel with these guys, right? So this and this will cancel with this and this. And all you're going to be left with is this portion in yellow. Okay, and you could combine those terms. So the y double prime plus 25y part is going to end up equaling all that yellow stuff. Combining those, it'd be 10, negative 10 a sine 5t. Let's make sure I'm still recording my sound. Hello, hello, yep. And then plus 10 b cosine 5t, and we want that to equal 10 sine 5t, right? Okay, so equate coefficients. So I see I have negative 10a on one side and then 10 on the other. And then the b portion, the 10b, just there's no cosine on the right, so it will just be equal to 0. So a will be negative 1 and b will be 0. So finally our solution is y sub c plus y sub p. So y will equal y sub c, c1 cosine 5t plus c2 sine 5t, and then plus this y sub p portion with a and b filled in. So I guess it would be minus in this case, right? So it's going to be minus 1 times t cosine of 5t, and then plus 0. And that would be your solution. Okay. I think on the final exam, I'm going to make that worth extra points, so you just can't blow this off and say, ooh, I'm not going to do that extra work. Nope, I'm going to make it worth plus 10 on the finals, so make sure you know how to do these. Okay, moving on, then we get into chapter 7 material. Of course, there was applications. I'm going to assume you did your homework, though. Looking at problems like 11 to 16, first off, and I'm only going to put 7.1 to 7.3 on the test, so I'm not going to bother with the delta Dirac thing or the convolutions. I don't think I'll be putting those on the test. So just 7.1 to 7.3. So let's take a look at a couple of those. Okay, so I expect you to be able to do anything that I gave you on a quiz from 7.1. So you have to be able to do Laplace transforms, no notes, no helper stuff. So Laplace of this, of course, we have 4 times Laplace of t squared is s cubed in the denominator with 2 factorial up top. You don't have to simplify that. Minus 3 times 5 all over s squared plus 25. Okay, let's try. So you should be able to do any Laplace transform. And then finally in 7.2, we have enough work with transforms in order to kind of solve differential equations. So looking at problems like 1 to 15, and then 17 to 22, any of those are fair game. So, right, so first just start you off easy with a transform here, Laplace inverse of 1 all over s cubed plus 3s. Okay, so for this guy you're going to have to do a partial fractions, which I hope you're able to do by now. If not, how did you do your homework? So anyways, this will be, you can rewrite the denominator by factoring it. So it's 1 all over s times s squared plus 3. So I have a linear factor, so I need one fraction for that with a constant up top. And then irreducible quadratic, s squared plus 3 with bs plus c in the top. Multiply through to get rid of the denominators, so I get 1 equals a times s squared plus 3 plus bs plus c times s. I'll equate coefficients, so I have as squared plus 3a plus b s squared plus cs. And then I can say the coefficients on the s squares, a plus b must equal 0. There's no s squared on the right, or sorry, on the left. Then the s terms, there's no s on the right, so c must be 0. And then the constant term 3a equals 1, so at least I get a is 1/3. And then b equals negative a from the first equation, so b must be negative 1/3. Okay, so I rewrite the stuff in that transform. So I get Laplace inverse of 1/3 all over s, and then plus negative 1/3 s all over s squared plus 3, and then plus 0. So this will be 1/3 times 1. Laplace inverse of 1 over s is just 1. And then minus 1/3, and that's a cosine. Cosine of the square root of 3t. Okay. Okay. So you should be able to do any kind of thing that maybe was on a quiz from 7.2. Then you should also be able to do differential equations using these transforms. So y prime minus y equals 2 cosine of 3t with an initial condition y of 0 is 0. Okay, so transforming everything, I get s Laplace of y minus y of 0, which is 0, minus Laplace of y equals 2 times s all over s squared plus 9. So doing a little factoring, I have s minus 1 times Laplace of y equals apparently 2s all over s squared plus 9. Solve for the Laplace of y. So I get 2s all over s minus 1 times s squared plus 9. Then you need to do partial fractions on that. Okay, so 2s all over s minus 1 times s squared plus 9. So partial fractions, this will be constant all over the linear plus this linear over a quadratic. Multiply through to get rid of the fractions. You get 2s equals a times s squared plus 9 plus bs plus c times s minus 1. Okay. So this will be 2s equals as squared plus 9a plus bs squared minus bs plus cs minus c. You're equating coefficients now, so you have a plus b is 0. Then you have negative b plus c equals 2. Then you have 9a minus c equals 0. Okay, so how do we want to do this? Well, let's solve for c. So c is equal to 9a, and then this will be negative b plus 9a equals 2. And then take this equation and add it to the first equation, right? So you'd have 9a minus b equals 2. So you get 10a equals 2, so a would be 2/10, which is the same as 1/5. So c is going to equal 9/5, and then of course b is just negative a, so it would be negative 1/5. Okay, so quarantine all that off. Now I'm looking for y equals Laplace inverse of a 1/5 all over s minus 1 minus, and you always want to kind of split these up, right? You want to split the bs plus c over s squared plus 9, because one will be a cosine, the other one will be a sine, right? So have minus 1/5 s all over s squared plus 9. You're going to need a factor in there to make it, because you need a, well, not this one, but the next one you're going to need a 3 in the numerator, right? So you have plus 9/5 all over s squared plus 9. So you get y equals 1/5 y equals 1/5 e to the t minus 1/5 cosine of 3t. And then for this last one, you need to introduce another factor of 1 over 3 for it to work, right? Because you kind of need to smush in a 3 in the numerator. Okay, so you get y equals 1/5 e to the t minus 1/5 cosine of 3t plus 3/5 sine of 3t. And that'd be it. That'd be your answer there. Okay, let's move into the last section I'm going to put on the final then, 7.3. And problems like 1 to 23 and then 26 to 33 are fair game. The piecewise, what we call it, the unit, the Heaviside function, is that what we're calling it? I keep screwing up the name of that. I apologize. The unit step function, okay, but it's like a piecewise function. We're going to be using that here, of course. Anyways, the first kind of thing you dealt with was translations on the s-axis. So let's do a problem with a translation in it. I have y prime plus 4y equals e to negative 4t, where y of 0 is equal to 3. Okay, so these translations on s-axis was for things like if you had 1 all over, you need the Laplace of 1 all over s minus 3 squared plus 4, something like that, right? And you could just say, this is Laplace inverse, this would be the same as Laplace inverse of 1 all over s squared plus 4 with this translation, s goes to s minus 3, and you would pop out an e to the 3t and then just do the transform of what's left over. So I hope you remember that stuff. If not, go back and review it. So let's do that here, right? So I got the Laplace transform of y prime. That will be s times Laplace of y minus y of 0, which is 3, plus 4 Laplace of y. On the other side, Laplace of e to the negative 4t is going to be 1 all over s minus negative 4 or s plus 4. Okay. So collecting the Laplaces together, I'll have s plus 4 times Laplace of y. Move the 3 to the other side, I get 3 plus 1 all over s plus 4. Divide by s plus 4, so Laplace of y is going to be 3 all over s plus 4 plus 1 all over s plus 4 squared. Okay, so that's going to be a translation there. And so y is equal to, the first one I can just do in my head, 3e to the negative 4t plus Laplace transform of this thing, which will just be 1 all over s squared with a translation, s goes to s plus 4. Okay, so you'll have y equals 3e to the negative 4t plus, and you could pop out an e to the negative 4t and just do, and this is an inverse Laplace, sorry, inverse Laplace of 1 over s squared. And so that's going to give you 3e to the negative 4t plus inverse Laplace of 1 over s squared is t, so you get t e to the negative 4t. Okay. From there, then we saw the piecewise, the unit step function, or I think they were calling it the Heaviside function in the book. So number 19, you should be able to do Laplace transforms of these things going back and forth. Cosine 6t, unit step function of t minus pi. So in this direction, into the s direction, what you have to do is first pop out this part with an exponential, e to negative pi s, and then do the Laplace of cosine of 6, but you translate the t on the t-axis. Now you go t plus pi. You just do the opposite sign of whatever the Heaviside thing is doing, right? the t minus pi. Let's make sure I'm using that correctly. It's the Heaviside function, right? Of course, it's going to sign me out. You're not signed in anymore, buddy. It's going to be a jerk about it. Let me pause the video. Yeah, it's the Heaviside function. I'm sure in the video I called it something weird, or I forgot what it was called. Unit step function, Heaviside function. Okay, so you're going to have to translate this then, or I don't know how you're going to do the transform of it, using the couscous formula that I told you in class. So this is basically cosine of 6t plus 6 pi. The couscous formula says cosine 6t, cosine 6 pi, then minus sine 6t, sine 6 pi. This part will be 0 because sine of 6 pi is 0. This part will just be cosine of 6t because cosine of 6 pi is 1. So you have e to the negative pi s times the Laplace of cosine of 6t, which we should be able to do. That's just e to the negative pi s times cosine, so s all over s squared plus 36. Okay, let's look at one final question then, a differential equation with Heaviside functions. Problem 32, y double prime plus 4y equals sine of t times the Heaviside of t minus 2 pi. Okay, Laplace we need initial conditions as well then. So y of 0 is 1, and then y prime of 0 is 0. Okay, Laplace transform of everything, so I have s squared Laplace of y minus s times y of 0, that's 1, minus y prime of 0, which is 0, plus 4 Laplace of y, and then the Laplace of this thing, I can pop out an e to the negative 2 pi s, and then I'm left with the Laplace of sine of t plus 2 pi. Right, so t plus 2 pi. Same sine formula. This thing would be sine t cosine 2 pi plus cosine t sine 2 pi. This part would be 0. Sine of 2 pi is 0. This part is just sine t. Okay, so I have then collecting the Laplaces together, s squared plus 4, Laplace y. This is 0. This is just s, so I can add that to the other side. It's negative s, and so it'll be a plus s on the other side. Have e to the negative 2 pi s times the Laplace of sine t, which is just going to be 1 all over s squared plus 1, and then plus the s from the other side. Divide both sides by s squared plus 4. You're going to get e to the negative 2 pi s all over s squared plus 1 times s squared plus 4. Plus something that's going to turn into a cosine of 2t. Okay, and then I need to do the inverses, but I need to do a partial fractions first. So, 1 all over s squared plus 1 times s squared plus 4 is as plus b all over s squared plus 1 plus cs plus d all over s squared plus 4, multiplying through. 1 equals as plus b times s squared plus 4 plus cs plus d times s squared plus 1. So 1 equals as cubed plus 4as plus bs squared plus 4b plus cs cubed plus cs plus ds squared plus d. Okay. I'm just kind of checking my work. Okay, so the cubed guys, a plus c is 0 apparently. So a is negative c if you wish. The squared guys, b plus d is 0. So you can say b is negative d if you wish. The s guys, so you get 4a plus c is 0. That's going to mean A and C are 0 right there, because if you use this, you'll have negative 4c plus c is 0, so negative 3c is 0, so c is equal to 0, and therefore A is also equal to 0. Okay. Then the last equation, 4b plus d is 1. So you use this equation, replace b with negative d, so negative 4d plus d is 1, so negative 3d is 1, so d is negative 1/3, and of course then b will be positive 1/3. Okay, so let's quarantine that. I need to do a Laplace inverse now, so y equals Laplace inverse of all of this jazz. So I have e to the negative 2 pi s, should become a Heaviside function, times a0 plus b is 1/3 all over s squared plus 1, plus c, which is 0s, and then plus d, so minus 1/3 all over s squared plus 4, and then plus the s all over s squared plus 4. Alrighty then, I'm going to move this downwards, give myself a little more room. Okay, so the first two guys are going to be shifts on the, I guess, the t-axis, because there's those Heaviside things. So the first one, there's a 1/3, and then it's going to be sine of t, but kind of minus something, right? So we have a Heaviside from the e to the negative 2 pi s of t minus 2 pi, and so this will be t minus 2 pi as well. And then minus 1/3, but I need an extra factor for the numerator of 2, so it'd be 1/6, I believe. Then sine of t minus pi, and then Heaviside of t minus pi. 2 pi, those are both 2 pi again. So what the heck's the difference between those two? Oh, one has a 2, the second one has a 2 in front of the t. Whoops, let me erase that a bit. So this would have been 2 times t minus 2 pi, like that. Okay, and then the last guy, of course, is a cosine plus cosine of 2t. Finally, then, clean up these parts with the same sign formula. So here, this will be sine t cosine 2 pi, and then minus 0. So that's just going to be sine t. So I have y equals 1/3 sine t Heaviside of t minus 2 pi. Then this part is sine of 2t minus 4 pi. And of course, same sign formula, sine 2t cosine 4 pi minus 0, because sine of 4 pi will be 0. So this will just be sine of 2t. So minus 1/6 sine of 2t, and then finally plus this cosine part, the cosine 2t. And that will do it. As usual, thank you for watching. I hope you had a good semester, and I hope you do well in the future. All right, have a good one. Whoops, I made a mistake, didn't I? Not so fast. I forgot part of it. I forgot the stupid Heaviside. I apologize. I hope you stayed to the end and you didn't just cut off the video. It's a mistake there, sorry. Anyways, now thank you for watching, and well, you just make a triple sure that's correct, because I got the cosine 2t. It's 1/6 t minus 2 pi sine 2t, and then the 1/3 sine t. Okay, so now it's right. I'm so sorry. Thank you for watching, and I'll see you later.